Hello everyone, my name is Xin Gao and you can call me Jacob. And today I'm going to talk about my honors project, which my topic is Torus, calculus, and the geometric of manifolds. So to begin with, I want to talk a little bit about why I choose this manifolds. When I was considering all different types like sphere or even the Mobius strips, I was like, which one I related the most? Well, somehow I was kind of hungry that day, so a Taurus looks like a donut, then Taurus it is. And it's kind of fun. Let's begin. So this is the agenda of my presentation today. So we have 6 agenda. We're going to start with the definition of a torus. We talk about the parameterization of the torus equation. And then we'll look at the tangent space, the tangent plane geometric. Then we'll see the gradient vectors fields. We see the vectors, we see the gradient, the vector fields, and then we'll calculate the surface interval. Finally, we're gonna see some real-life implementation of torus, such as in buildings, architectures. Let's begin. Definition of a torus. Well, it's not hard to understand torus, right? It's just a donut. It's basically any donuts that you can buy in any donut shop. Well, the mathematical definition of a torus is, it's also kind of easy. It's basically 2 radius, the big R and the small r. The big R rotates around the z-axis, and then the small r rotates about the big R. So it's kind of like using this circle, and it goes around this circle track, and it forms a donut shape. The big R is the shape of the donut, and the small r is the tube of the donut. Okay, that's the definition of the torus, and we'll understand it more when we parameterize it. Okay, let's go to the second part where the parameterization begins. All right, let's talk about parameterization. I choose to use u and v as my parameters, so we can rewrite this equation for the vector for the torus a little easier, so we can know exactly, we can describe exactly each point on this circle, and also it makes the calculation a lot easier. So what I do to begin with is that I define u as the angle in the xy plane, this xy plane, and where it rotates around the z-axis. So this is the u is the angle, and it goes around the z-axis, the big R. And then I define the v is the angle inside this tube, so the small r, when it rotates around the big R, I define this angle v that goes positively towards the z-axis and then goes around. So you'll see that the domain of these parameters are both from 0 to 2 pi, and then here also from 0 to 2 pi. And we use these 2 parameters to describe the x, y, z coordinate systems, and then we can tell exactly where we're describing. So for example, x is the r, right? The big R plus the r cosine v. So the cosine v, and then times the cosine u, where we can get the x. And also when we go to the y, when we go rotate to the y, things doesn't change, only u changed. So we go to sine u, and then the z-axis is simply just the height of this donut, right? So it's just the small r times sine v. That's it. So the parameterization is kind of easy, and we're going to use this a lot. This is our based function. Okay, so this is the parameterization of the torus. Well, this word always gets me. It's kind of hard to say, huh? Now we go to the tangent space geometry. We're going to talk about tangent vectors first. We begin with take the first derivative of the function we just got from this one, and then we're gonna take the partial derivative of this function in respect of u and in respect of v. So it will give us this two vector that we're gonna use it a lot to help us find like the tangent plane or like the surface area and so on and so forth. This is very useful. We're gonna use this tu and tv a lot. And tu is basically just the partial derivative of x in respect of u, and tv is the partial derivative of x in respect of v. Then that's it. So we can see this is like when you go down very, very narrow, then you'll get this space that's defined by these two vectors. Okay, let's keep going. The tangent plane. So we're trying to get the equation of the tangent plane, and how we know that the equation of the tangent plane is where the normal vector v is perpendicular, so its dot product with any vector on the tangent plane will be 0. Okay, so what we need to do now is simply to find the normal vector n. And to find the normal vector n, we just need to get the cross product of tu and tv. And we just need to get the simplified result of normal vector. I will explain about the normal vector more in the later section 5. So here I just gonna give it the solution already, but don't worry, later I'm gonna show the steps of how to find the normal vector n here. But it's basically the cross product of these two vectors, and we already have these two. Let me kind of go back a little bit and talk about tangent plane. Tangent plane is just a plane that interact with one point of this surface, right? So it has one point, and its normal vector is perpendicular or orthogonal with any vector, with the tangent plane or any vector that is lie on the tangent plane. So the point normal equation of we can just find this, like we can find this point ABC, and this ABC is just this from this simplified normal vector n. Then you can just simply plug in this, and we'll get the equation of the tangent plane, which is this, and equals to 0. That's how we find the equation of the tangent plane. You can see from the picture here, this is the green arrow is the normal vector, and then this red vector and then blue vector, tu, tv. That's the two vectors. Okay, perfect. Let's move on. And we're going to talk about the gradient vector fields. So we talk about the gradient vector fields starting from considering the scalar field f defined by the z coordinate, which is the f of x, y, z equals to z, or r sine v. We just take the gradient vector, the gradient of f equals to the partial derivative of f in respect of x, the partial derivative of f in respect of y, the partial derivative of f in respect of z. And then we just get this vector that's 0, 0, 1. And what is this? Is very, I think you will definitely understand, it's just along on the z-axis and pointing upwards. The gradient vector field on the surface is the orthogonal projection of the ambient gradient onto the tangent plane at each point. This vector field always points in the direction of the greatest rate of increase of the scalar field f along of the surface. The tangent gradient is found by subtracting the component of that is normal of to the surface. So this is the equation. That's what it's saying. The gradient of the surface of f. So it's the gradient of f subtract this thing, the component. This is the tangent gradient. Okay, and then where this n means the unique normal vector that it's simply the cross product of TUTV divided by the magnitude of TUTV. And this resulting field will show vectors circulating upwards the top of the torus where z is maximized, and downwards the bottom where z is minimal. So you can see this arrows pointing upwards at the top and pointing downwards at the bottom in these two pictures. Now let's talk about the surface integral. Very interesting. So basically we're using f of x equal to 1 over the surface. So this is the function of the area of the torus, right? So we're calculating the area of the torus, and we can do it just by doing the double integral over the domain 0 to 2 pi and 0 to 2 pi. The magnitude of the cross product, which is n. This is n, right? DUTV cross product is n, so this is the length of n, and DUDV. And we already know these two vectors. Now we're gonna find the n. This is the part where I say earlier I'm gonna explain how to find n. Here we go. So n is the normal vector. N is the matrix of the cross product of these two vectors, right? So we just need to do this calculation here, and we can do it by factor out the common term c. So this two thing r, big R plus R cosine v, we take it out, we replace it with a c, so we make it easier to write in this way, in this way of writing the vector. And we can just factor out r and substitute c. So here we got this. This is the vector of the normal vector, and we factored this two thing out. We factored the c and the r out, and then we substitute the c back to r, big R plus R cosine v. Then this is the normal vector. Now we just need to find the length, which is the magnitude of this normal vector. And you can do it by this. Well, you can see this is just the formula of how to find the magnitude. Note that we're using the trigonometry identity, the basic, this cosine square theta plus r square theta equals to 1, which you all know. And here we can just simplify everything inside here. You can see that we organize it, we simplify it. This is 1, this is 1, and then this is 1. So this is just 1. So the magnitude of normal vector is simply r times big R plus R cosine v. That's it. And thus the surface area element ds, what we need to do with ds is just r br plus R cosine v du dv. Okay, now let's get back to calculating the integral of the surface, which is the area of the torus. Okay, so now we have the length of the normal vector. We can now do this. We have this function here. It's just the double integral over the domain, and this is the length of the normal vector du dv. Okay, now this is the easy part where we can start by just doing du, because in this function there's no u here, so we can know that it's just simply 2 pi times this function here. And now we do the integrate in respect with v. Now we did the integrate in respect of u. Now we do v, and we can just do that. We take this out, and then we separate these two parts and take the integration. Well, this is not too hard. This is just 2 pi, and this is 0. So eventually we get the surface area of the torus is just 4 pi square big R small r. That's the integration. Okay, finally, we're going to talk about some real-life implementation of torus. The first thing that comes to my mind was architectures, the buildings that using this special shape to demonstrate their engineering ability or for tourist reasons. With one of the most famous example would be the Museum of Future in Dubai, which is the picture on the left side. You can see, well, this is not a perfect torus because, well, it's not even, but it still kind of follow the same idea. It has the big R and then the small R, it goes around. That makes it a tube, like a donut shape. And then this is more on the right side in China, the Sheraton Guangzhou Hot Spring Resort. It's more of a typical torus, even though it doesn't have the bottom end of a torus, but still, this is like a pretty big donut. One thing I noticed, which is kind of interesting, kind of not related, but you see they like to build this kind of shape next to water. So when it reflects on the water surface, it's like a figure of 8 or infinity, which is beautiful. Perhaps that's the reason why they build this. But you can see that, of course, this is not easy to build, but architectures, construction companies, they can apply this mathematical manifolds into real life. And that's why I think this is very interesting to learn about the mathematical functions, calculations behind this manifold. Okay, that's it about my honors project about Torus. Thank you very much for your listening, and I will see you soon.